What questions do you have? Things are going all right? All right, well, let's finish up this section on inner products and then get into a process for creating a special type of basis. So, we're going through a couple of these properties last time, and I mentioned these are all about restating things in terms of, for the distance properties, it's all about restating things in terms of the dot product, or the inner product, if you will, for the distance ones. I do want to talk about the number 4 here that we talked about right at the end of class. I said that you should try to give that one a go. It'll involve the Cauchy-Schwarz inequality, but I just want to go through it real quick. I said start with the magnitude squared. And again, how do we, when we have the magnitude squared, what does that equal to? Yeah, the inner product with itself, right? So it would have the inner product of u plus v with itself. And then we also talked about how we can basically do a FOIL type of thing, right? So this would be inner product of u with itself. You'd have 2 inner products of u and v, and you'd have the inner product of v with itself, right? We did one like that last time, right? Where it kind of just looks like a foiling idea, doesn't it? Forgot to snooze my watch. Okay. All right. Remember last time we also talked about the Cauchy-Schwarz inequality. I'll write it off to the side, where that said that for any inner product space, the absolute value is always less than or equal to the product of the magnitudes. Right? Got it. Go away. This stage, I've got the inner product of u and v. I would like to replace that with the product of the magnitudes of u and v. But notice I need an absolute value, correct? But of course, if I replace this with the absolute value, does it get smaller or does it get bigger? Or I guess, let me ask it this way, could it get smaller if I replace it with the absolute value? No. If it's positive, it stays the same. If it's negative, I make it bigger, right? So if I replace that with the absolute value, I get an inequality that goes this direction. And I would have 2 times the absolute value of the inner product. Now, looking at the 2 that are kind of sandwiching that in, how can I rewrite the inner product of u with itself?
Magnitude squared.
Yeah, that's the magnitude squared, right? And then the same thing on this side. Now that I have the absolute value of the inner product, I can replace that with the product of the magnitudes. It's less than or equal to, but that's already the direction my inequality is pointing, isn't it? So if I replace it, it's still less than or equal to. Oops, forgot my magnitude signs here. So I replace that with 2 times the magnitude of u times the magnitude of v. And now this should look like x squared plus 2xy plus y squared. I can refactor that, can't I? That factors as magnitude of u plus magnitude of v, the whole thing squared. And now look what we have following the chain of stuff that we've got going on here. I started here, right? I've got equals, less than or equal to, less than or equal to, equals. So at this point, I've got this piece is less than or equal to that piece. Take the square root of both sides and you get what you want here, right? Okay. This is known as the triangle inequality, probably something that you've learned a long time ago. The reason why it's called triangle inequality is that if I've got a vector u and then a vector v, I can represent their sum going that direction, can't I? And what do you know about triangles? What happens if you take the sum of any two sides? It has to be at least as big as the third, which is exactly what that says. So that's the triangle inequality. And notice that that's exactly a restatement in number 8 here. Same idea. It's basically the same idea. Again, as the distance is defined in terms of magnitude. So you use this is also the triangle, also called the triangle inequality. So again, I just wanted to go through that. It gives you a little application of Cauchy-Schwarz besides the whole idea of making angle measure being well defined. And it wasn't that bad of a proof. Okay. Questions on that at all? This is pretty typical in math when you're trying to show an inequality. Replacing something with a known inequality or a known quantity that's either bigger or smaller, depending on which way you're trying to go with your inequality. Okay. So we did that in a couple places, right? We did that here when we replaced with absolute value, and we did this here using Cauchy-Schwarz. Let's go on to do an example of angle measure that's a little bit using a little bit different inner product. We'll just do one of these and not both. I'll leave the other one for practice. We've talked a little bit about how this integral of the product of two functions defines an inner product on a function space, in particular the continuous functions from -1 to 1. And we've talked about what our formula is for our cosine of the angle of between two vectors in any inner product space. Cauchy-Schwarz inequality, again, guarantees that my top in absolute value is no bigger than the bottom. So that quantity is always between -1 and 1, which allows me to do the inverse cosine. Okay. This works for any inner product space. Okay. So in this case, if I want to find the angle between the functions p of x equals 1 and q of x equals x, I'm going to follow this inner product and just do it. Okay. All right. So if I do the inner product of p of x and q of x, what function are we going to integrate? What's p of x? And what's it, q of x? So what are we going to integrate? X dx, right? I could do the work, but do you know the answer with just by looking at it? It's 0, isn't it? It's x is an odd function, and we're going around an interval that's symmetric about 0, right? Yeah, I mean, you can do 1/2 x squared and plug in your endpoints, you're still going to get 0. But in this case, I do get 0, which means it doesn't matter what the magnitude of p and q are. What's your cosine of theta going to equal? 0, so theta must be 90 degrees, yeah. Now, I know it's a little bit strange because we think 90 degrees, we think perpendicular, right? These are not perpendicular to each other, are they? P of x equals 1 would look like that. Q of x equals x look like that. Those are not perpendicular lines, are they? No. We see this, again, this is relative to how we're defining the inner product. It does not correspond to Euclidean perpendicularity. Okay? That was a fun word to say. It's a lot of syllables. Okay? Does not tell, when we get 90 degrees, that's just telling us something about what's the relationship between these two functions relative to the inner product, not perpendicular in a Euclidean sense. Okay? So don't try to equate those two. They equate when you're talking about regular Euclidean vectors and regular dot product. They don't necessarily equate in any other sense. Okay? However, the idea of being 90 degrees from each other in an angle sense really does matter later on with what we're going to talk about today. Okay? All right. Let's do the other one because it's not too bad to do, obviously. If I do P of X and Q of X again, if I do that inner product, in this case, what function are we going to integrate? Yeah, the 3/4 x squared. That'll give me what? 1/4 x cubed when we do our antiderivative. And you'll get a half when you're done. Because I get a 1/4 minus a minus 1/4. So that'll be the numerator of our fraction for trying to figure out our angle between the two vectors. The other pieces that we need are the lengths, right? The magnitudes, the norms, whatever word you want to use. We need to know the magnitude of each of those. To do the magnitudes again, we'll do the inner product of the vector with itself, and then we'll take the square root at the end. Okay. What function are we going to integrate if we're going to do the inner product of P of X with itself? 1. That was pretty easy. Get 2, don't we? Okay. So what is the magnitude of P of X then? Square root of 2, good, because I got to take the square root of that inner product with itself, right? Okay. What function are we going to integrate when we do the inner product of R of X with itself? What's it going to be? 3/4 x squared and then the whole thing squared, right? So I got to multiply by itself. So we get a 9/16 x to the 4th. We get there 9/80 x to the 5th. So you get 9/40 when you're done. And then again, to find the magnitude, what do we need to do to that? Square root it again. Okay. Is it 2√10 on the bottom? Ooh, that doesn't sound good. So then, if we're going to figure out the angle, we're going to use that cosine formula again. The inner product was a half. The magnitude of P of X is √2. And the magnitude of R of X is 3/2√10. I get square root of 5/3 when we finally simplify all of that mess. Feels like the square root of 5/3. Looks like I did it okay. All right, and then to figure out theta, what would you do? Inverse cosine, good. 5's a little bit bigger than 2, so that's a little bit bigger than 2/3. Oh, goodness. What are you going to get? Something around 50 some odd degrees. But then I'm done. It's between inverse cosine. Oh, somewhere around there. Should be between 30 and 60, definitely. Actually, I think I may have lied. It may be bigger than 50. No, I don't know. What'd you get?
41.
41. Okay. Well, yeah, I was thinking of inverse sine instead of cosine. 41-ish. Yeah. Okay. How would I, regardless of whether or not I knew what the value is without a calculator, I could have looked at this and said that it was acute versus obtuse because why? It's positive. Right? Should be able to definitely see that part. This part I would expect a calculator at that point.
Question. So what we did on the left hand side with the 9 degrees didn't matter.
It didn't matter what these were because the top was 0. Yeah. The top 0 doesn't matter what the bottom is.
So the how
Let's be the inner product. Oh, that should have been an R, not a Q. Yeah, that should have been an R. Yep. I'm sorry. Yeah, the inner product goes on top and the magnitudes go on bottom. Yep. Okay. All right. Any questions on the computations at all? And that was all calculus things or easy or calculus things, right? All right. Again, like Jolly just pointed out, I didn't need to do any work here, right? I knew that there was going to be 90 degrees because the inner product was 0, right? And that's going to give us our definition here in the next part is that they're orthogonal if the inner product of the two vectors is 0. We're going to have this definition. I know that if you've taken Calc 3, you use this to talk about, pardon me, perpendicular vectors if their dot product is 0. We're extending that notion to any inner product space. Any inner product space, we refer to them as orthogonal if the inner product is 0, and that's, again, like I said, going to help us out in the next section here in a few minutes. All right. But to do a pretty quick example of this, these are vectors in R3. And unless you are told otherwise, if you've got a familiar vector space, assume it has the usual inner product on it. Okay. In particular, if you've got your Rn vectors, Euclidean vectors, assume it's just your regular old inner product. If you've got functions, assume it's got integral inner product. Okay. And it'll always tell you on what interval you're talking about doing that integral over. So these are Euclidean vectors. You're not told there's any strange inner product, so we're assuming it's a regular old inner product. So what do I want to do to solve this problem? It says find all values of k so that the vectors are orthogonal. What do you want to do? Do the dot product and set it equal to 0, right? What is the dot product of these two things? Okay, so you get 3 times the k minus 4 plus the k times the k plus the -2 times the -7. That's just your regular old inner product, right? Take your product of your components, add them up. If we simplify, we get k squared plus 3k. I've got a minus 12 and a plus 14, so I've got a plus 2. So we get k squared plus 3k plus 2 equals 0. Looks like I made that one factored nicely. K plus 1, k plus 2. And so your k is -1 or -2. But in particular, nothing in particular fancy about this particular problem. It's just the idea of trying to reinforce that if you're talking about vectors being orthogonal, you need the inner product to be 0. All right. To go along with orthogonality, we need the idea of orthogonal projection, which is easier to visualize in Euclidean space, in particular R2 and R3, than it is to visualize in other spaces, but it's still an important concept in other spaces. All right. So let's talk about how we get projection. What we mean by orthogonal projection in the Euclidean sense is that if you've got V1 and I want to project V2 onto V1, then I'm going to take the tip of V2, I'm going to construct that perpendicular line going this way. Wherever that intersects, that's the vector I'm going to use along V1 to refer to as the projection, okay? This is why we call it orthogonal projection, by the way. right? I'm using the perpendicular sense this way, doing that intersection here and just drawing that vector. So notice that the projection of V2 onto V1 is either in the same direction as V1, or if my vector is pointing this way, it could be in the opposite direction of V1. Okay. Basically, the projection is an idea of how much in the V1 direction does V2 go. Okay. So let's come up with a formula using the Euclidean sense, and then we're going to use this same formula to extend to any inner product space. Okay. And this is just a little bit of right triangle trig. Okay. If I want to figure out the length of this side, and I know what this angle is here, what trig function would you use? If I know this angle and say this vector here, the length of that side, what trig function would you use to help you figure out that red line? Cosine, right? Okay. In particular, the cosine of theta has to be what? It has to be whatever the length of, I'm going to call it, I'm just going to call it x for the time being, and I'm going to solve for x. It'll be x, which would be the length of that side, over the hypotenuse, which would be the length of V2, isn't it? We agree with that? Okay. We have a formula. If I'm given V1 and V2, we have a formula for the cosine, don't we? The formula for the cosine is the inner product of the two vectors divided by the magnitude, the product of the magnitudes of the two vectors, right? We agree with that? Okay. Pardon me. Now I can figure out what x is. Multiply both sides by magnitude of V2. Notice that goes away. You get inner product of V1, V2 over the magnitude of V1. Okay? This is the length of that red vector, right? Red on my screen is definitely not red on your paper. I wasn't going to pay for color printing out of my department budget for it. Okay? All right. So that red length is that x, right? Okay? It could be negative. I mean, we wrote it as a length, right? But it could be negative because I have to define in terms of the inner product, right? That's why I said signed length of that. So the signed length of the projection is called the component of V2, oops, along V1. Okay, that's what it's called. The actual, if it's negative, it could be negative, but it's the length of that projection vector. Okay, it could be negative if it's pointing in the other direction. We call that the component. Same idea if you think about components of vectors in the Euclidean sense, right? You have an x direction, a y direction, maybe a z direction in R3. We call those components, don't we? Those would be the projections in the lengths of the projections in the x direction, in the y direction, or in the z direction. That's what we call them components. It's the same idea. Okay. All right. So now let's talk about the formula for the projection. Well, I want the actual vector. The projection is a vector. The vector points either in the same direction as V1 or in the opposite direction as V1. Okay, I have the length, but I just need to make sure I have the direction. Well, V1 gives me the direction, but I can't just take that number and multiply it by V1 necessarily, because that might make the vector too big or too small, depending on how long V1 is. So what should I do to V1, do you think, to standardize the length? Make the unit vector. How do you make a unit vector in the same direction? Yeah, multiply divided by the magnitude, right? Good. So our formula for the projection of V2 onto V1 will be use the length that we just came up with, and then multiply that length by the unit vector that goes in the V1 direction. That's how we found the unit vector in the V1 direction, isn't it? Okay. Notice on bottom, you're going to get magnitude squared. What's another way to write magnitude squared? And the product with itself. Good. So this is your projection formula for V2 onto V1 in any inner product space. It doesn't have to be Euclidean. Okay? If you've had Calc 3, you've probably seen this formula before with dot products, right? Literally the same formula. No difference at all. Okay? We're just using the fancy bracket notation. That okay? Notice that when you do V2 onto V1, the only place where V2 actually appears in the formula is in the dot product on top, right? Everywhere else there's a V1. Let's see if we can put this formula to work in a Euclidean sense, and then we'll talk about how we might do it in a different sense in a little bit. We've got the projection of V2 onto V1 if we have these two Euclidean vectors. I tried to make the picture. This one that has the little thicker dashed line here, that's the 2, -1, 6. The 1, 7, 3 is this black one that's pointing in this direction. And so I put in the line between the tips that would show you where the projection goes. So this short little vector should be the projection. Okay. All right, so when we compute this then, if I want the projection of V2 onto V1, what goes on top? The dot product. So I'd have 2 minus 7 plus 18 on top. What goes on bottom? Inner product of V1 with itself, right? So we'll have 4 plus 1 plus 36. When we do the inner product of V1 with itself. And we multiply that by what? V1. Good. 2, -1, 6. So we get 13 on top and 41 on bottom, it looks like. Thirteen over 41 is a little bit less than a third, because 13 over 39 would be a third. Right? And this looks like, if I just look at my picture, if I do 1, 2, 3 of those, I get a little bit less than a third, right? A little 3 and a little bit more. That okay? 2 times 1, -1 times 7, 6 times 13. Or times 3, I'm sorry. I'm just doing the dot product of V1 and V2. That okay? All right. So let's let's continue on with this idea of orthogonality, but move it up to the idea of subspaces and bases. So that's what's going on in the next section here. To concept of orthonormal bases, talk about why we care, and then talk about how we can create them. Okay? So, to that end, let's define what we mean by an orthogonal set and an orthonormal set, and then talk about orthogonal complements a little bit. So if we just take a subset of vectors, we refer to that subset as being an orthogonal subset, as if whenever V1, I'll call it just V and W. V and W are in S with V not equal to W, then V, and W are orthogonal. Pick two, well, all this says is pick two vectors out of your set, as long as you don't pick the same vector twice. If I take any two vectors, again, as long as I don't pick it twice, they must be orthogonal to each other. To give an easy example of that, in R3, you're used to writing everything in terms of I, J, and K. If I just take the vectors I, J, K, that would be an orthogonal set. Because I and J are orthogonal to each other, I and K are orthogonal to each other, J and K are orthogonal to each other. Right? So those are orthogonal. To do orthonormal, well, I see the word norm in there. Norm refers to magnitude, right? So if it's an orthonormal set, an orthogonal set is orthonormal if each vector in S has magnitude or norm 1. Okay. It has to be, it can't be orthonormal without being orthogonal. So that's condition 1. Orthonormal just adds the extra condition of every vector having length 1. Okay. So to give you an easy example of something that's orthogonal but not orthonormal would be start with your ijk again, but maybe multiplying each by 2. Then each of them would have length 2, but they're still all orthogonal to each other. So that would be orthogonal but not orthonormal. IJK forms an orthonormal set because IJ and K all have length 1. Okay? So that's the difference between the two. So let's look at these two examples. Yes?
From the council.
Mhm.
Does that mean that every time V is different from W, then the dot product will give us 0?
That's exactly right. That's exactly what we're going to do in this example. Yep. Okay. All right. Let's look at this first example. First, can this one be orthonormal? No. In particular, which vector easily has a length other than 1 without having to do any work?
0.
0, 0, 5, right? That has length 5, doesn't it? So that can't be orthonormal. But let's see that it is orthogonal. To check that it is orthogonal, we're going to use the idea that the inner product is 0. Okay? So we'll take all the possible pairs of inner products here. So if I do 1, 2, 0 dotted with -4, 2, 0, I get -4 plus 4 plus 0 gives me 0. Do the same thing with 1, 2, 0 and 0, 0, 5. And do the same thing with -4, 2, 0 and 0, 0, 5. All of those pairwise dot products that we could possibly take gave us 0. So S is orthogonal, but the magnitude, just like you said a second ago, the magnitude of that particular vector is not 1. So S is not orthonormal. Oops. Yes.
How about the others? The others is the length 1.
I'm sorry? That doesn't matter. All of them have to be length 1 if it's orthonormal. So if I find just one that's not length 1, I'm done. For it to be orthonormal, every single vector in the set has to have length 1. I found one that doesn't, so it doesn't matter. I don't care if the other two are 1. They could be. It still wouldn't be orthonormal.
See, just to see the A, vector if it was like 0 is just 1.
But if it's zero, about zeros and just a constant, then it has to be the absolute value of that constant. Yeah. Yep. Those are easy ones to do. Um, just by looking, without doing any work, what can I say about the norms of each of the three vectors in the next example? Not what the value is, but what can I tell easily about the norms of each of the three vectors in the next example? They're equal, right? I just mixed around the components, didn't I? They're certainly all going to have the same length, right? Because there's one component that has a 1/3 and two components that has the 2/3, right? Remember when you're doing your lengths of these things in the Euclidean sense, you'll square each of the components so the negatives don't matter, right? For the lengths. So these will have exactly the same lengths. So if I do one length, I did them all, don't I? What is the length of the first vector? I bet it's 1. Otherwise, it'd be a really bad example, right? Square root of a ninth plus 4/9 plus 4/9 gives me 1. So all of them are going to have length 1 because they all have the same length. You can check pretty quickly, okay? I'm not going to go through all of the inner products, but if I do the first one, they all should work, by the way. If I do the first one, oops, you would get -2/3 plus -2/3 plus 4/3, and I really do get 0. And you can check the other two. So you really do get an orthonormal set here. I didn't check all of it, but I checked it. You can check it. I'll leave that part to you. Okay. All right. Let's look at the next one. Why do we, tells us a little bit about why we care about orthogonal sets. This one says that as long as you don't put 0 in the set, which 0 is going to be orthogonal to everything by definition. Remember, our definition of orthogonal is that you have an inner product of 0. We already showed that the inner product of the 0 vector with any vector is 0, right? So by definition, your 0 vector is orthogonal to everything. Okay? But it's not going to help you with linear independence, right? So I don't want to throw that in a set and say something about linear independence, but as long as that's not in my set, then I do get a linearly independent set. Let's see why. Okay? So let's let, I don't know how to do that sometimes. Let's let our S be V1, V2, out to Vn. If it's going to be linearly independent, what linear combination in particular do I need to worry about? A linear combination that gives us what? For linear independence. What linear combination in particular are we interested in? The one that gives us the 0 vector, right? All right, okay. So let's suppose that we have that linear combination that gives me the 0 vector. What are we assuming about S? It's orthogonal, right? So if I were to dot product this expression with, say, V1, what would happen? If I took V1 and dotted it with this whole thing, what's going to happen? Well, nothing's really going to happen to this one, but what's going to happen to every other term in your sum? It's 0, right? Okay. Now think again about linear independence. What am I trying to show that every single constant has to be?
Zero.
Zero at this point, right? So here's what we're going to do. We're going to take any v sub I in S. Then we would have v sub I. I'm going to use the dot notation. Technically, I should use the inner product notation, but it's a pain in the butt to write. Okay, so C1 V1 plus C2 V2 plus Cn Vn equals Vi dotted with 0. But what did you say? Anything dotted with a 0 vector is? 0, right? So I'll get the number 0 here. Using our properties of dot product or inner product, I can distribute the dot product over each term in the sum, and we can pull the constants out in front, right? What's the only term that would be left? Well, if I is not 1, it kills that one off, right? If I is not 2, it kills that one off. It's going to kill every single thing off except the ith term, right? So when we're done, we'll have C sub I, Vi dotted with itself equals 0. Well, what kind of a set are we starting with? What are we assuming S is? Orthogonal. What does orthogonal mean? The dot product is 0 as long as they're different vectors, right? This vector is different from all of them except in one spot. So you've got a bunch of zeros added together, but this one's not 0 necessarily. Right? That's how I got that. I just distributed it through. And it's going to kill off everything except for one term. What vector are we assuming is not in S? 0 vector. So what can't this be?
0.
0. So what does this have to be? 0. Good. So since Vi is not the 0 vector, we see Ci must be 0. I was arbitrary, right? Doesn't matter which I you choose, that's always going to happen, right? So hence C1, C2, all the way out to Cn has to be 0. So S is orthogonal. Orthogonal sets are always linearly independent so long as you don't throw the 0 vector. Okay? Orthogonal sets are always linearly independent. Okay? So if your orthogonal set is big enough, gets to the dimension of your vector space, then you get a basis. Okay? That's where we're going with this, by the way. Right? We're trying to create a special type of basis. Okay? All right. So that gives us the idea of orthogonal set. So then the idea of orthogonal basis is if S is a basis for a vector space, it's an orthogonal basis so long as S is an orthogonal set. So it's a basis in which every single vector is orthogonal to the rest of them in the set, much like IJK, right? IJK forms an orthogonal basis for R3. Okay? But we've also seen things that aren't orthogonal bases, right? For example, if you use 1, 0 and 1, 1 in R2, that forms a basis for R2, but it's not orthogonal because 1, 0 and 1, 1 are not orthogonal to each other. Okay. What do you think the definition of orthonormal basis is then? S must be a basis and also be orthonormal, right? Everything has to be magnitude 1, exactly. So if S is a basis for V and S is orthonormal. let's look at this. We've already seen that this example is an orthogonal set, right? That was the first example we did. We saw that this is an orthogonal set, right? Is the zero vector in there? Not a fair question. Nope. So the zero vector is not in there, so we know it's automatically linearly independent, and it has 3 elements, right? Okay. Where are these vectors coming from? R3, dimension of R3 is 3. So it's a linearly independent set of size 3. So if it's linearly independent, it also has to span in that case. So it automatically becomes a basis, right? So we have a basis for R3 here. So this is, I'll just write it all down, what I just wrote down. S is orthogonal in R3. Okay, so that tells me that S is a linearly independent set of 3 vectors in R3, and the dimension of R3 is 3, right? So S is an orthogonal basis for R3. Once it's orthogonal, and once it has the right size, we get its basis, right? Okay. Yes.
You do what you talked about not having a zero vector.
Say that again.
You could have what you talked about not having the zero vector in.
Because of any set with a zero vector in it can't be linearly independent. That's why. Yep. Notice same thing happens with the second example here, except that it's orthonormal, right? From what we did before. So this is an orthonormal. If I can spell the word normal, that would be helpful. Orthonormal basis for R3. Because we already saw that each of them, it was orthogonal and everything has length 1. So our goal with this going forward is going to talk about how do we create orthonormal bases from regular ones. And the idea is, why do we care? So let me write that down, why we care. Okay? Here's the why we care, and then we'll talk briefly, and then we'll talk about the how to find these things. So let's suppose that we start with S as an orthogonal basis. And let me give it some names here. Let's call it V1, V2, out to Vn. For a vector space V, and let W be in V. I said for a vector space V, in this section I need inner products. Okay, so assume we got an inner product defined. Since it's a basis, how can we write W in terms of the V's? If I know that I have a basis, how can I write any other vector in terms of the basis? As a linear combination, right? Our goal here is to try to figure out what the C's are, right? Remember we talked about coordinates with respect to a basis? The C's are those coordinates, okay? We're going to try to figure out a formula for the C's if we have an orthonormal basis. Just like what we did in the previous part, I'm going to just take the dot product or the inner product with one of the V sub i's with W. If I do that on the left-hand side, what are you going to end up with on the right-hand side from what we just did in the previous example?
CI times the dot product.
Fantastic. It's orthogonal, so it kills everything off except for one of them, doesn't it? All right? So what's your CI? It's just VI times W over VI times, or dot product with VI. So notice that your coordinates you can find in terms of the dot product. In particular, notice that this would be the coefficient on the projection onto the VI, wouldn't it? So your this is why we care. Your coordinates are basically the coefficient on the projection onto each basis vector. If it's orthonormal, what happens to this part? It's 1. Yeah. So notice that to find your coordinates with respect to an orthonormal basis, all I have to do is take your vector and dot it with each of the vectors in the basis, and I know what the coordinates are. Which makes it really easy. Okay? This is why we care. Okay? This is important for why we care if we're doing approximations of things relatively quickly later on. Okay? One of the things we're going to talk about are doing function approximations with trig functions, with sines and cosines in particular. And this will pop up there. All right? This is why we care. All right, so what we'll talk about next time is how to find orthogonal, orthonormal bases once we've been given a basis. All right, so we'll talk about that next time.